Yeah, hello. We are going to watch video 10 of the statistics. Were you really thinking I was going to speak in that voice the whole time? When performing a one-sided hypothesis test, keep in mind that the sign that we get from calculating our test statistic, our Z or T score, is now important. We don't chop it off like we used to do with confidence intervals. So we are going to follow the quote-unquote fourth step process from the book, which is basically our stating our hypotheses, defining our parameter, and then completing the three C's of conditions, calculations, and conclusions. So the example we're going to look at is caffeine, a chemical found in many popular beverages, is known for reducing fatigue. A college student wants to investigate his daily caffeine intake from beverages such as soft drinks, energy drinks, teas, and coffees, etc. Beverages that this particular student consumes daily. If he becomes convinced that he consumes over 500 milligrams of caffeine per day, then he will change his habits. Here is his daily caffeine consumption in milligrams for 14 days. Perform a significance test at the alpha equals 0.05 level. So number one, we need to state some hypotheses. So our null and alternate hypothesis. Since we are dealing with a mean level problem, then we are going to be using mu. And the value that we are wanting to see whether we exceed or not is the 500 milligrams. So if we're at 500 milligrams, or technically less, but we're not going to write less, then we're not going to change our habits. If we are over 500 milligrams of caffeine per day, then the college student will change his habits. Okay, why 500 milligrams? Who knows? Maybe he read something that said that over 500 milligrams of caffeine on average daily is bad and may lead to adverse health effects. Who knows? So mu is our mean amount of caffeine consumed daily. And then I'll also put my units that we're measuring this in, which is in milligrams. On to conditions. Number one, random. Do we have a random sample? It didn't really say that our 14 days were random. So, were these 14 consecutive days? Um, did he maybe do it every Monday? Did he, record it every other day? We don't really know. So this is going to be one of those instances where we're going to say doesn't mention sample is random. So we will assume it is, but proceed with caution. Now, I told you we would not do the problem if, for instance, the data was collected by a sampling technique that involved a high level amount of bias. For example, like a volunteer response or like a call-in poll, somehow where your data is definitely going to be skewed or overestimated, underestimated in some way. I don't think we have enough evidence here to say that these 14 days maybe aren't representative of his daily caffeine consumption. So we'll just assume that this is random and we'll proceed like it is. Number two, the independent. Is the population at least 10 times our sample size? All right, well, our population would be really all days. And is that greater than or equal to 10 times our 14 days, which is 140? Sure. I mean, all days, are we talking like in a year? Are we talking about in a lifetime? We don't really know specifically how many days we're supposed to be looking at in general, but we can definitely just say assume true and move on. Now, for the normal condition, keep in mind for mean level problems, it's not really normal, but we're really checking for T. Now, is the population known to be normal? We don't know that. Do we have a big enough sample size that we can use the central limit theorem? 14. No, it's not bigger than 30. So what do we have to do at this point? We need to put our data into a list. So if you want to do this to kind of double check, you certainly can. Put all these numbers into list 1. And then go to your second y equals, which is your stat plot. Make sure one of them is turned on. Select the box plot, really the modified box plot that allows for outliers to be shown, which I believe is the first option that you should come across. And use list 1 or whatever list you used. And then again, you're going to have to do zoom 9 after it fully loads so that you get a picture that looks like this. I took this directly off my calculator, so it should look exactly like what you should see on yours. It might be scaled bigger or smaller depending, probably smaller, but this is the idea here. Now, two things we need to look for. Are there any outliers? There are 0 outliers present. Again, if there was an outlier, you would see some dots maybe, out here, or you might see some dots out here, but there are none present. Another thing we need to look for is strong skewness. Do we think that there is any strong skewness going on in our box plot? I really don't think so. So we can say, based on our box plot of our data, there is no outliers. There are no outliers, sorry, English people. There are no outliers, nor any strong skewness. So we may assume T procedures. Check. Okay, so there's all of our conditions. Part 3, calculations. Now, we need to calculate a test statistic, in this case a t-score, and the formula based on the last video was this. And so our x bar, we need to know what is the sample mean of all of our days here. Well, I've already kind of done that. You can, if you already put these numbers into list 1, then you could go to stat, over to calc, and then one variable statistics. And then you should get this screen right here. And here's our x bar value, which is 622 point, and I'm going to go 4 sig figs, so 0.9. And I'm going to subtract away my hypothesized mean value, which was our 500. Our S is our sample standard deviation, and again, you always use the S sub x. Never use this sigma sub x. Okay, so we're going to use 266.1 divided by the square root of n, and our n is our 14 values. So if I put that to my calculator, I should end up with a t-score, this is my test statistic again, of 1.723. So now, from my test statistic, I need to calculate the p-value. So we need to find what is the probability that we obtain a t-score that is as extreme or more extreme than our 1.723. And again, the reason why I'm saying greater than is because my alternate hypothesis was greater than 500 milligrams. So what I've done here, let me go ahead and write this. TCDF, my lower bound would be 1.723 to infinity, and then degrees of freedom we said was one away from our sample size. So the degrees of freedom will be 13 in this case. And I should get a p-value of 0.05387. And now we need to compare this to our alpha value, which I mentioned up here is 5%. So alpha equals 0.05. Is this really true that our p-value is less than our alpha value? We would say no, it is certainly not. Therefore, we would fail to reject the null hypothesis. We can't get rid of the hoe. Now, what I did over here was I can do this hypothesis test in my calculator, and I can do it just to kind of verify the numbers that I'm getting here. Okay, and if you look at the bottom of your, the front page of your notes, I've got a little box there that leads you to a few different pages that shows you how to do hypothesis testing with proportions and with means. So, here's the t-value. There's my test statistic. Here's my p-value right here. And then here's the sample mean and the sample standard deviation values that I used right here. And then the 500, hey, that's what I'm using right there. And the 14, hey, that's what I'm using right there. So if I punch all this in my calculator, it's giving me every number that I need or will calculate in my calculations. And whenever you do the t-test here, on the bottom, it'll give you the option to calculate, and this is the screen up here to calculate, or it gives you the option, and it says draw, and then it'll give you this picture. So you can even see what type of picture you need to draw for this step right here. Since you use TCDF, you technically have to use a picture. And you could just copy down the picture that's in your calculator. Oh, too far away. So here is our 1.72, and I rounded it to 1.723. They got 1.7. Oh, yeah. No, my bad. All the way back here. This really should be, what, an 8? My bad. I don't know how to round. That should be an 8. That should be an 8. My bad, peeps. I'm sorry. I make mistakes sometimes. I admit my faults. But still, this is all we should get in here. This is our picture. This represents a little over 5%, which isn't quite enough to let us reject the null hypothesis. So our conclusion, we would write, we do not have enough evidence at the alpha equals 0.05 level to conclude the mean amount of caffeine consumed, I'll say in milligrams, is more than 500. Or I could put the milligrams here and not leave it there. You pick. So we do not have enough evidence to go with the alternate hypothesis, basically. And that is our conclusion. It was very close, but not enough to say that it really differs from 500. Okay, because we only had 14 days out of, a very large amount of days that we could measure caffeine intake. And we're just a little on the, on the higher side of our 500. Now, the examples in the book that I want you to just kind of look at if you would like, they start getting a little long because these problems are very long. So, at any point, just pause through these, read them, and then, start playing the video, look at the next one, because there are quite a few different parts here. I mean, here's just part 1, part 2. Then here's all the calculation stuff, and here's the conclusion. Here's what I got from my calculator. And then here's the one problem that I would like you to do and bring to class so that you can get some more practice on this. Okay, so let me scroll this up because there is another number hiding under here. And that is really all for this video. So good luck. Please do this problem. We will do it the next day in class. And adios.